by dy. So the integrals, again, they work out. We could do those integrals. They're not impossible. They're pretty simple as well. But just look at how much extra work and how much extra thought went into it because I didn't choose wisely. Okay? So it is worth your time to think about how these choices are going to affect your answer and make it easier on you. Okay, so your turn. Any method. You get to set it up. What method would you do here? Find the volume obtained by rotating this graph about the x-axis, and we'll reconvene and see what method people were choosing. Okay, so if we had to start this question, again, you're always going to start with the picture. So let's, before we make any decisions, let's get a good graph happening. So this is roughly what that parabola looks like. Okay, and it says it's revolving it around the x-axis, so it's going this way. And this is a function of x, so that means what I would like is I would like to use dx. Dx, again, is the vertical bar. It's becoming sliced thinner and thinner. So in my picture, this is what one of those bars might look like. Okay. This is going to be rotated. It is perpendicular, so this means we're going to use the disk method. There are no holes in that graph when it rotates, so it is not a washer. It is the disk method, perpendicular, no hole in the center. Okay? So to set this one up, to use the disk method, it's circles that we're slicing up. So that area for each circle is pi r squared. We want to add up all the slices, so it's going to be pi. The bounds here go from -4 to 4. Of the radius squared. So this is the radius. When I rotate it, this piece here is the radius. It's on the graph 1 minus x squared over 16. So 1 minus x squared over 16 would be the integral that would get us this area. Okay. Any questions about how we picked that or how it came out?
So what's the difference between using 2 pi r squared and pi r squared?
The difference between?
Using 2 pi r squared and pi r squared.
We never use 2 pi r squared, right? Because 2 pi...
2 pi r, sorry.
So 2 pi r h. Pi r squared is when we're using circles, because that's the area for our disks that we've sliced up. Or we're using the washer method when it's big R and little r, and it's pi big radius squared minus little radius squared. Okay, but we're using 2 pi r h when we have cylinders. So the shell of a cylinder, like that piece of paper that that's a terrible cylinder. I don't know why I always expect myself to be able to do good ones, but well, at least it's a little bit better. So, anyways, so if this is the radius of the shell that's being spun around, then when I unravel it, it has 2 pi r, the diameter for width, and h for the height. So the area of each of the shells is 2 pi r h. That's why we use 2 pi r h on the shells. Okay? Okay, so this one, clearly, I'll tell you ahead of time, the shell method is better than the disk method. So see if you can figure out how to do this using your shell method. Okay, so this one's a little trickier. If you've been looking at your picture, you're going to notice that since we're rotating it around the line x equals 2, it changes the problem a little. But hopefully we can still work together on this one. So picture as number 1. Let's get a good picture started here. I kind of have something that looks like, well, let me put a few points on here. So at 1, it's going to be 3. At 0, it's going to be 1. And it sort of does kind of like that. And it says, I also have the line y equals 1. So that's going to be here. And I have the line x equals 1, which is here. So the area that I'm looking at is this figure inside there. Now, one more important piece of information I've already highlighted is that we're rotating it around x equals 2. So this is actually where I'm going to draw my rotation. Whoops. And like I said, I still like to do to actually draw it to remind myself. I'm rotating it around that line. Okay, so now I have my picture set up. I haven't made any decisions yet as to what I'm going to do, I guess other than the fact that I told you to use the shell method. But let's just pretend we didn't have the information given to us. Again, what we would like to do is say this is a function on x. I would love it if I could use dx in my problem. That means I'm going to have vertical bars. So let's put a vertical bar on and see what happens. Okay. Now, this position I'm at, this is any old shell, remember? I mean, maybe it looks like 3/4, but we need to come up with a function for any old rectangle shell that we want. So any old shell would be at position x, right? Anywhere in there, that's the location is x. Okay. So if its location is x, and I'm rotating it around this line right here, okay, then what's the radius? Okay. The radius is going to go from this bar out to the shell. So how far is that? How could we describe the radius? Close. 2 minus x. So the value here is 2. The value here is x. The distance between them is 2 minus x. So my radius function this time is 2 minus x. And when they're tricky like that, I suggest you try a couple points just to make sure it's correct. At 0, it would have a full radius of 2. So it would go all the way there. That's correct. At 1, it would have a radius of 1, which is also correct. You know, a half, it would be 1.5. So this model works. That is the radius for any shell that I put on that rotation. Okay? Now we also need a height. So what's the height function going to be this time? That's, if I do this piece, okay, so this piece here is x cubed plus x plus 1. And that means I'd be taking this entire shell all the way down to the axes, right down to there. Okay, but I don't want that part.
Divided by 2.
Divided by 2. Yeah, x, so I'm going to subtract 1 because this is the line y equals 1. So to get rid of it, what I'm going to do is say it's this piece, which is the top, minus 1, which is the bottom. So then that way I'm removing all that out of it, and I just have the bar in my picture. Okay, so that's my radius function, that's my height. One nice thing is it actually cancels one term out, so I end up with an easier height. So to integrate this, okay, it's in terms of x. So what are my bounds? What are the bounds for my integral? Yeah, it goes here from 0 to 1. It is 2 pi, the radius function, which is 2 minus x, times the height function, which is x cubed plus x. Okay, so that's enough. That would get us the volume if we revolve that figure around the line y equals 2. Okay, now one thing that some people ask me at this point, so I don't know if you're thinking about it or maybe you're just ignoring it, is what about the gap here? Right? We kind of have a washer method. It's sort of like, you know, we couldn't just do disks all the time. When there was a gap, we had to worry about, you know, what's going to happen in here, all this area, when I do that. Well, the shell, if you picture a shell, it already has a hole in it. So unless we choose to fill the hole by going all the way to x equals 2, my bounds stop at 1. That means we're leaving a hole in the middle of it anyways. So that's another nice feature of the shell method. We only have to integrate from here to here. That hole is already going to be in the picture just by the way a shell is made, right? So anyways, enough of the shell method for today. Hopefully both of them are a little clearer for working with.